Hello, my name is George Gunter. In this video, I'll be telling you about my research through the CAT vehicle program at the University of Arizona, which focuses around applications to autonomous vehicles. Before I get into talking about my actual research, I want to talk first about what are autonomous vehicles. Wikipedia defines an autonomous vehicle as one that is capable of sensing its environment and navigating without human input. I actually really like this example. It's concise, and it mentions sensing as an important part of the autonomous vehicle. While there are not fully autonomous vehicles commercially available right now, there are cars with advanced sensing capabilities available on the road. Let's look at a popular example, the Tesla Model S. This footage is taken from a video by Wired magazine which describes the sensors found on the Model S. Placed around the vehicle are 12 ultrasound sensors used for accurate detection of close-by objects. In the front of the car is a radar which allows the car to look far ahead of it, as well as a forward-facing camera. While it's true that fully autonomous vehicles are not commercially available as of yet, there have been successful experiments with them. Let's look at an example. Here's a video from Stanford-based company Drive.ai, where they demonstrate an autonomously equipped vehicle driving around on a rainy night. If you look, it appears that the car uses a three-dimensional LiDAR sensing capability, probably located on top of the car to map its surroundings. Now that we've seen what autonomous vehicles look like, let's look inside a real one, the CAT vehicle. The CAT vehicle has several dedicated computers on board just for processing the data from the different sensors. Additionally, on top of the car is a three-dimensional LiDAR scanner from the company Velodyne. This is the car as a whole. Now in front of the car is a two-dimensional SICK LiDAR scanner. My primary research concern has been to develop an algorithm by which the CAT vehicle can sense and then track both the position and velocity of other vehicles on the road. In order to do so, I employ a technique that's common to control theory known as the linear Kalman filter. Let's look at an example. Here a point mass moves along a sinusoidal path, but with random Gaussian noise of standard deviation 1, making it vary from the clean path. The Kalman filter tracks this position. Both the point mass and the Kalman filter follow along the sinusoidal path, but the Kalman filter smooths out some of the randomness that you see in the point mass. The Kalman filter additionally calculates the particle's velocity. It's important to note here that the Kalman filter needs no information about the particle's velocity in order to derive it. It needs only position data. Let's now consider the same example, but with randomness of standard deviation 5. This is a much more chaotic path, but note that the Kalman filter is less affected by the randomness than the particle itself, following a more smooth distribution. Again, the Kalman filter tracks the velocity of the particle, this time with more randomness, but still to some extent following the true nature of the particle. Okay, now that we've seen an example, let's move on to actually looking at some results about how this performs. In an initial test of how the Kalman filter could estimate position, data from a series of previously performed tests was run through the algorithm, and the Kalman filter's estimate of where a nearest car to the CAT vehicle is compared to camera-verified data, seen in the graph. As you can see, the filter performed quite well, almost matching exactly the verified data. However, position is not the only thing that I'm interested in measuring. Velocity is also important here. As a result, a second experiment was put in place. In order to test measuring another vehicle's velocity, the CAT vehicle is parked at rest, and a second vehicle is driven by first in one direction, and then back again in the opposite direction. We can see here what the car sees through its two-dimensional LiDAR sensor. Red dots indicate where the car detects an object. Additionally, through the use of a clustering algorithm, the car makes guesses about where it thinks other cars might be in its environment. Let's now watch as the car crosses the parking lot. And back again the other way. Let's now look at the estimated velocity as the car accelerates across the parking lot. And again, back the other way. Now obviously, these results are not perfect. Due to the inherent inaccuracies of the two-dimensional LiDAR data, the car has a difficult time determining what are other vehicles in its environment if the environment is chaotic. Now the car does have three-dimensional LiDAR data, which we would like to take advantage of. However, under our current computational methods, that data is too dense. There's too much of it. As a result, in future work, we would like to develop a method by which we can incorporate this three-dimensional LiDAR data into our analysis, as well as to set up more clean tests to try and analyze the results of our tracking algorithm. Thank you for watching.